Okay, so let's just introduce some terminology just so that we're all clear. We're going to talk about a K-stage pipeline. Okay, and a K-stage pipeline, okay, is an acyclic circle, so that we're not going to talk about cycles in the graph. Inputs sort of flow across the pipe, in one end and out the other, and we're not going to, at this stage, deal with complications when there's feedback from a later pipeline stage to an earlier pipeline stage. So it's an acyclic circuit, and it has exactly K registers on every path from input to output. So that you can just count them. You just look at all the paths and say, oh, like on that previous one, the diagram on the previous page, what sort of pipeline is that? That would be a two-pipeline, a two-stage pipeline, because there were two registers in every path from input to output. Okay, and if we're, usually academics sort of get a thrill out of notation, and so we can talk about a zero-stage pipeline, and that would be a combinational circuit because there's no registers along any path. We're going to adopt the convention of putting registers on the output. Always put a register on output. So a one-stage pipeline always has a single registers on all the outputs. Okay, no other registers. So that's what it would be a one-stage pipeline. And remember, I talked about, we can have the opposite convention if we want, but we'll do the output register convention, and that will then allow us to compose pipeline circuits and still end up with a legitimately pipelined larger circuit. Okay, and then we choose the clock so that it has a period sufficient to cover the slowest computation that any pipeline stage has to do. So there's sort of a notion of a bottleneck in our pipeline. We find the slowest pipeline stage and say, okay, everybody's going to have to wait for that guy to finish. And we'll talk about how to improve on that here in a couple slides. So the latency of So we have this clock period that we've chosen to accommodate the slowest pipeline stage. And the latency of a pipeline circuit, of a K pipeline circuit, is always K times that clock period. And the throughput is always 1 over that clock period. Everybody sort of happy with that? I mean, this is just sort of writing down the terminology I've been using for the last 15 minutes. Okay, let's look at this circuit, which I'm here to tell you is a bad job of pipelining. So for what value of K is this a K pipeline? And the answer, everybody should be sort of shaking their head and going, well, this doesn't take a lot of, here's a path that involves 2 registers. Here's another path that involves 2 registers. But here's a path that only involves 1 register. So this is, in fact, not a well-formed pipeline. Okay, why? What's sort of bad about it? I mean, other than that, our definition sort of helps us understand that it's not well formed because there's no K that describes this as a K pipeline. But what's sort of bad about it just from it gets the wrong answer point of view? So first, let me just make sure we're clear about what the right answer is. The right answer is the answer that would have been produced by the combinational circuit if we applied the inputs one at a time and waited for the output. After TBD, got the answer out of the output. So this circuit does not get the same answer as an unpipelined circuit. So yes? Right. Right, so basically what you're saying is that we're mixing generations of inputs. Right, that's the trouble here. Look at the B module. It's in a particular clock cycle, notice that the value that's coming in on its Y input down here has already been delayed by a cycle, but delayed by that register. Okay, but the X value that's coming through the A is of the current generation. So we're mixing generations, and typically mixing generations of data will almost certainly cause the pipeline to get a different answer, right? Because I'm mixing, y sub 0 and x sub 1, and I'm doing a computation involving those, when I should have been in the B module computing with x sub 0 and y sub 0, right? So that's a K pipeline keeps all the generations of data in a particular processing stage the same. Everybody sort of happy with that? Okay, and so the notion is that this particular ill-formed pipeline is ill-formed because there's not the same number of registers along any path from inputs to outputs. And so this particular circuit will in fact mix generations of data and produce different answers. And we wouldn't be very happy buying this from anybody saying, look, your throughput is much better. And forget the fact that half your instructions aren't working, but it's doing it at 2 billion times a second. Isn't that great? And you sort of go, no, actually it's not. Okay. So in a well-formed pipeline, we're never going to mix generations of data. And that's what it means to be well-formed. So you might ask yourself, are there techniques I can use to build a well-formed pipeline? And we'll talk about those in a second.